Chemistry, Chapter 13, Ions in Solution. Section 1, Objectives. Write equations for the dissolution of soluble ionic compounds in water. Predict whether a precipitate will form when the solution of soluble ionic compounds are combined, and write net ionic equations for the precipitation reactions. Compare dissociation of ionic compounds with the ionization of molecular compounds. Draw the structure of the hydronium ion and explain why it is used to represent the hydrogen ion in solution, and then distinguish between strong electrolytes and weak electrolytes. Compounds in aqueous solutions. Our main idea is ions separate from each other when ionic compounds are dissolved in water. So when a compound that is made up of ions, like those whose names are listed in the ion sheet that you are memorizing, dissolves in water, the ions separate from one another. This separation of ions that occurs when an ionic compound dissolves is called dissociation. The ions are no longer attached to each other, they are separated from each other. They are no longer associate, they dissociate. In our first example here, sodium chloride, a solid, dissolves in water and dissociates to form a sodium ion and a chloride ion. The AQ after each of the ions indicates that it has been dissociated in its solvent. Calcium chloride, also a solid, dissolves in water, and when it separates the ions, it will separate out to one calcium ion and two chloride ions. Notice that the number of ions produced per formula unit in the above is not the same. One formula unit of sodium chloride gives 2 ions in solution, where one formula unit of calcium chloride gives 3 ions in solution. In this picture, we see a beaker of water and some salt that has been dumped in the bottom of it, and on a submicroscopic level we have the sodium chloride down at the bottom of the enlarged view, and then we have the water molecules represented by a red ball with 2 little white or blue things attached to it. That's 2 hydrogens attached to an oxygen. The hydrogen end is positive and the oxygen end is negative, and you can see that the water molecules have their positive ends facing toward the green chloride ion, and the positive or negative end of the water molecules is attracted to the positive purple sodium ions. When we have a dissociation taking place, we're going to assume that it is 100%, that none of the original formula unit is present. None of the ions are still sticking together. They have now been dissociated completely. A solution that contains 1 mole of sodium chloride contains 1 mole of sodium ions and 1 mole of chloride ions. And in our book, we're going to assume that there is 100% dissociation for all soluble ionic compounds. If it's insoluble, that's a different story. But if they're soluble, we're going to assume it's 100% and it's complete. So that a solution that contains 1 mole of calcium chloride contains 1 mole of calcium ions and 2 moles of chloride ions, for a total of 3 moles of ions. In our sample problem here, we're going to write the equation for the dissociation of aluminum sulfate in water, and then we're going to determine how many moles of aluminum ions and sulfate ions are produced by dissolving 1 mole of aluminum sulfate, and then what is the total number of moles of ions produced by dissolving 1 mole of aluminum sulfate. So first of all, we got to write the equation for the dissociation of aluminum sulfate in water, following the example for sodium chloride and calcium chloride. So here is our aluminum sulfate. Notice that the two ions within aluminum sulfate are the aluminum ion and the sulfate ion. And in order to balance the equation, on the right we have to put a coefficient in front of the aluminum ions because there are 2 aluminums on each side, and then when we look at the sulfate on the left in parentheses, we see that there's 3 of them. So we need to have 3 sulfate ions, and we indicate that they're dissociated with the aqueous that are after them. So how many moles of aluminum ions and sulfate ions are produced by dissolving 1 mole of aluminum sulfate? Well, if you look at the right side of the equation, we can answer that question. We have 2 moles of aluminum ions, indicated by the coefficient of 2 in front of Al, and we have 3 moles of sulfate ions, indicated by the coefficient 3 in front of the sulfate ions. So what's the total number of moles of ions produced by 1 mole of aluminum sulfate? Well, if we have 1 mole of aluminum sulfate on the left, we now have 2 moles of aluminum ions on the right, and we also have 3 moles of sulfate ions on the right, for a total of 5 moles of ions. So now let's take this information and apply it to precipitation reactions. These precipitation reactions are like those that you did when you performed your lab to create 2 grams of a substance by reacting 2 ionic compounds. So although no ionic compound is completely insoluble, compounds of very low solubility can be considered insoluble for most practical purposes. So to determine which substances those are that are soluble and which are insoluble, we have this chart to give us that kind of information quickly. Let's look at it in a little more detail. Number 1, sodium, potassium, and ammonium compounds are soluble in water. So if it is a compound that begins with sodium, potassium, or ammonium, it's going to be soluble in water. Number 2, nitrates, acetates, and chlorates are soluble in water as well. That it doesn't matter what metal ion is in front of the nitrates, the acetates, or the chlorates, it's still going to be soluble. Number 3, most chlorides are soluble, not all of them, and the exceptions are silver chloride, mercury 1 chloride, and lead chloride. Now, lead 2 chloride happens to be soluble if you just make the water hot. If it's cold, it's insoluble. Okay. Number 4, most sulfates are soluble unless it's a sulfate of barium, strontium, lead, calcium, and mercury. If any of those sulfates, they're insoluble. If it's not one of those, it's soluble. Number 5, most carbonates, phosphates, and silicates are insoluble except those of sodium, potassium, and ammonium. So if it's a carbonate, like sodium carbonate, sodium phosphate, sodium silicate, are soluble. If it's not one of sodium, potassium, or ammonium, then it is insoluble, as it says. Number 6, most sulfides are insoluble except those of calcium, strontium, sodium, potassium, and ammonium. So like, for instance, calcium sulfide would be soluble. So Here is a chance to put what we know to work. Is calcium phosphate soluble or insoluble? So look at the chart, figure 1.3, and you will notice that it says most phosphates are insoluble. So calcium phosphate is not one of the exceptions listed, so it is insoluble. So that one has a two-part. You look at the phosphate and says it's insoluble, but there are exceptions, and it's not one of the exceptions. So dissociation equations cannot be written for insoluble compounds. So as we showed the formula unit broken up into individual ions, you cannot do that with a substance that's insoluble. You can write one, but it doesn't represent